Okay, so in this video we're going to take a look at the geometric series and see if we can figure out a general formula for it, for the nth partial sum, and then also see if we can figure out conditions under which it will either converge or diverge. The geometric series is extremely important, and they really don't emphasize how important it is in high school. People get to university not knowing how to find what the formula for the general term is, or for the nth partial sum, right? Not knowing when it converges, when it diverges, just not knowing the basics about the geometric series, which is really no good because it's just stupidly important. So not only is it applicable to things like financial math, compound interest, annuities, perpetuities, and the like, but also if you do a sequences in series unit in a Calc 2 course, so second half of a first year calculus course, when you start looking at series and whether they converge or diverge, and then Taylor series, Taylor polynomials, which are extremely important. It's really important to have a tool belt full of sort of examples. One of the things, and this is getting a little bit ahead, but I think it's really good to sort of just give you an idea of how important this is to know. If you want to show that a series converges, one of the main ways to do that is to compare it to other series. So comparing it to series which converge. If you want to show it diverges, you compare it to a series that is known to diverge. So you need to have sort of a stockpile in your mind of series that converge and that diverge. And the geometric series is just used over and over again. It's one of the standard examples, right? You'll be trying to show that a series converges. You'll be like, okay, I'm going to do some little computation here and show that it's less than or equal to this, which is less than or equal to a geometric series with this term for the R, and then it converges. So it's a really important basic thing that you need to know. You need to know about geometric series. So hopefully now you're sufficiently motivated enough to actually watch the video. Let's get into it. So here we have the nth partial sum of the geometric series. So of course the geometric sequence, right, is its first term. So the t is equal to 0 term is just a, and it's a times a hidden little r0 here. The first term, or the second term, the t sub 1, the one with an index of 1, is a times r to the power of 1. T2 is a r squared, etc. And then so Tn is a times r to the n. And this is the way they do it in university, right? Having the indices match, so we start counting at 0, which is a little bit sort of more rational. But in high school, it'll be sort of kicked back by 1, right? They'll say T1 is a, T2 is a r, etc. And then Tn is a times r to the n minus 1. So you'll have the power of the r lagging behind the index term. And so just to let you know, because when we get to the general formula, if you're like, wait, that isn't exactly what I saw in high school, this is why. In university, we start to count from 0 instead of 1 a lot of the time, and because it really makes things simpler and sort of more congruous. So that's what's going on here. So we have here the first partial or the nth partial sum, the first n terms of the geometric series. So this is t0 plus t1 all the way through plus tn, and these are the corresponding terms. And of course, a series is just when you add up the terms of a sequence. So that's what we've got here. This is the nth partial sum. And the first thing we're going to notice is that I can factor out an a, right? I can say Sn is a times 1 plus r squared all the way through r to the n. And 1 is, of course, r to the 0. And then we can just kind of ignore the a, right? In university courses, actually, you almost never include the a, because everything that you're going to do with the geometric series, you can just factor out, do that stuff, and then put it back in. So you may as well just assume the a is 1 if you have a situation where it's not 1. You just factor it out and then do all the stuff outside of the summation, right? You'll have like an a, and then the summation things going on with the indices, whatever, and then you just forget about it. So we put it in here just to take note of the fact that there can often be an a term, that the initial term, the a, does not have to be 1, but we may as well treat it like it is and kind of stick it back in at the end if we need to. Okay, so I'm just going to say this is 1 plus Sn is 1 plus r squared all the way through r to the n. And I want to figure out sort of a nice, convenient, compact way of expressing this And in particular, I want to find a way to express it that allows me to see when it converges or diverges. And if you remember, when we looked at the sum of the first n natural numbers, so 1 plus 2 plus all the way through n. The way that we figured out what the formula for that was we did this little trick, right, where we added the same sum in reverse. So we added n and then n minus 1 all the way through, and then n minus 2, there would be a 3 term there, etc. And we got n plus 1 plus n plus 1 all the way through n plus 1. And that was double the sum we were looking for. So we added the same sum again, and we got, well, this is 1 to n plus 1s, so this was n times n plus 1, and that gave us Sn is equal to n times n plus 1 over 2. And that was a cool little trick. We're going to do an even cooler trick here to figure out what is a nice expression, a way of expressing the geometric series. And we're going to we'll try to be sort of slow and deliberate about this, because I remember the first time I saw this, I found it really confusing. A lot of students sort of have to watch this a couple times. So I really encourage you to if you need to, stop and pause the video and really let this sink in. Stare at it for a while, do it yourself, right? Write it out, draw little arrows, make sure that you can sort of feel and understand why this works, because it's really important and really cool. So the trick that we're going to do is I'm going to take Sn, and sorry, when I say it's really important, not that this particular trick is used particularly often. I mean, it's a really handy trick. It can absolutely be used in other situations. But just that sort of that ability to see the cancellations, to see sort of down the road to see through those dots, so to speak. And you'll see what I mean in just a moment. That is a really, really important skill. That is something that it takes a little bit of time for your brain to start working that way. But it comes with practice and a little bit of patience. And it is really, really important to be able to see that kind of stuff, to sort of get used to thinking that way. Okay, so sorry, enough blathering about processes and math philosophy. What am I going to do? I'm getting ahead of myself. This cool trick is that I'm going to multiply. I'll do it without the brackets overlapping. 1 minus r. I'm going to multiply Sn by 1 minus r. I'm going to multiply both sides of this equation by 1 minus r, right? If these things are equal, then when I multiply them by 1 minus r, what I get is still going to be equal, right? If Sn was equal to all this stuff here, this sum, then 1 times Sn was going to be equal to all this stuff, which is great. Okay, and now this is the tricky bit. I'm going to think about what happens if when I multiply this in. I'm going to do some foiling here, right? I multiply that 1 in. It hits the 1, it gives me a 1. It hits the r, it gives me an r. It hits the r squared, it gives me an r squared. All the way it goes down, it hits there's an rn minus 1 right before the r to the n. It hits that, gives me an rn minus 1, and you'll see why I put that in just a second. And then finally it hits the rn, and it gives me the rn. It just reproduces. It reproduces this entire sum, multiplying it by the 1. That's great. What about when I multiply it by the r? This is a negative r, very importantly. It's a negative r. That comes in and multiplies by all this stuff. Well, the negative r multiplies by the negative 1 and gives me a negative r. It multiplies by the negative r and gives me a negative r squared. It keeps doing this, and I think you can hopefully see what I'm getting at here. It keeps hitting every power of r, bumping it up by 1 and making it negative. So it hits the r minus 2, or r to the n minus 2, rather, and gives me a negative r to the n minus 1. Then it hits the negative r to the n minus 1. It gives me a negative r to the n. And the last thing it does is it hits the r to the power of n and gives me a negative r to the n plus 1. That is what goes on when I multiply through, when I distribute that negative r through that entire sum. And of course, we have this very nice cancellation. The r cancels with the negative r. The r squared cancels with the negative r squared, etc. All the way through to the r to the n minus 1 cancels with the r to the n minus 1, rn cancels with the negative rn, and we end up with who survives at the end of this? Just the 1 and the negative r to the n plus 1. All I end up with is 1 minus r to the n plus 1. And that is a lot simpler than what we had up here, right? I've gone from having n terms to having 2 terms. But I haven't isolated the Sn yet, right? I'm looking for this sum, this nth partial sum, this general nth partial sum formula, which is what I was after in the first place. And so to do that, the same way that at the end of the baby Gauss sum of the first n natural numbers proof, I had to divide by 2. Here, now I have to divide by 1 minus r. So I end up with Sn is equal to 1 minus r to the n plus 1 over 1 minus r. And that's it. This is, and you've probably seen this formula somewhere before, but again, and I really can't stress this enough, although I probably get on people's nerves a little bit doing this so much, but it really is important. The process is what matters. Learning how to use tricks like this, how to think this kind of way, right? Look for these little sneaky things that you can do. This is the key to getting good at solving math problems, and really understanding what's going on. Taking the time to actually understand this stuff instead of just saying, okay, that's confusing, bunch of plus and minuses and canceling, I'm just going to remember the formula and move on. That is the key to remembering formulas, because if you can derive it yourself, you will never forget it, right? Our mind remembers processes, not data. So individual pieces of information, and it remembers relationships. And also you start to pick up these tricks, right? Math is a bag of tricks. As they say, as you get to the higher and higher levels, you pick up more and more tricks, and you can do cooler and cooler stuff, solve harder and harder problems. Okay, so that's great. That's the end of that sermon for now, I swear. S sub n is 1 minus r to the n plus 1. And why do we like this? Well, now I can tell when this converges, right? The whole thing, whether this converges, it depends on this term here. Let me do this in purple, maybe. Depends on this term, r to the n plus 1. Why? What's changing? The only thing that's changing is the n, right? As we get larger and larger partial sums, we go farther and farther along, we make the n larger, all that changes is the r to the n plus 1, right? The 1 is fixed, the r is fixed, r and a were fixed at the beginning, and then we forgot about a, but r is fixed. So the only thing that changes is the n, which means that the n plus 1 changes, which means that the r to the n plus 1 is the only thing that changes. And so we want to look at r to the n plus 1. What does this do as n goes to infinity? As n goes to infinity. What is this? Well, that depends on r, right? If r is bigger than 1, right? Say r is 2 or something, then r to the n plus 1 goes to infinity, right? It gets bigger and bigger and bigger. Now, as you make n bigger, r to the n plus 1 gets bigger. Say if r is negative 2, well, then the even indices, so when n is odd and r to the n plus 1 is even, those are going to get really big. Those are going to go up to infinity. And when they're odd, right? So r cubed, r to the 5, r to the 7, etc. So when n is even, so n plus 1 is odd, those are going to go to negative infinity. This thing is going to bounce back and forth between really positive and really negative numbers. So, but either way, the series is going to diverge. And by the way, if any of this seems weird, right, any of this stuff, we're talking about limits here. So if you're like, wait a second, what do you mean goes to infinity or anything like this? What do you mean by converges? The series converges. Do check out the videos on limits and on convergence of series. I probably should have recommended that at the beginning of the video, actually. But it should be pretty intuitive that if r is in between 1 and negative 1, then r to the n plus 1 goes to 0. So the limit as n goes to infinity of r to the n plus 1 is 0, right? If I take 1/2 and I square it, I get a 4th, right? I cube it, I get an 8th. I raise it to the 4th power, I get 1 over 16. It goes to 0. Same thing if it's negative 1 over 2, right? I get 1 over 4, negative 1 over 8, 1 over 16, negative 1 over 32, right? It goes to 0 in absolute value, right? It gets smaller and smaller and smaller in terms of absolute value, whether those are positive or negative numbers. It goes away. What is that condition? That condition is that r is in between -1 and 1, or a simpler way of writing that, absolute value of r is less than 1. So r is strictly in between -1 and 1, or the absolute value of r is less than 1. And that's it. That's my convergence criteria. The geometric series with a value of r, which is in between -1 and 1, absolute value of r is less than 1, this converges, right? It converges if r is bigger than or equal to 1 or less than or equal to -1, then it is going to diverge. The series is going to diverge. And by the way, if r is exactly equal to 1, right, we can't do this because we're dividing by 0. We have 1 minus r, but then this is just 1 plus 1 plus 1 squared plus all the way. So this series is just n, and that goes to infinity as n goes to infinity. So this is, and the last thing is we can figure out what the limit is. If absolute value of r is less than 1, then the limit as n goes to infinity of 1 minus r to the n plus 1 over 1 minus r is just going to be 1 over 1 minus r. And that's because the r to the n plus 1 term goes to 0. This goes to 0, and we get a finite limit. Otherwise, like I said, it's going to diverge. It's going to go up to infinity. So it's going to get arbitrarily large. There's no limit to how large it will get, or it's going to bounce back and forth in between arbitrarily large and arbitrarily negative numbers. Either way, it's going to diverge. So that's, and this is a really, really, really important thing to know. In the next video, I think we'll see some applications of this. This, like I said, it's extremely important. We're going to see endless applications of this, or seemingly endless applications of this. You will get sick of all the applications, but they're really, really cool. And again, like I do in all these videos, I really, really encourage everyone to go through these computations themselves, to learn how to actually do this. This is the best way to know that you understand something and to remember it and to be able to use it. If you want to solve problems involving this kind of thing, you need to be able to know how to do this, not just have the formula memorized. That's not enough. Please do take the time and get your hands dirty a little bit and dig in there and learn how to do these computations.